Good afternoon, this is Schweitzer, and we're going to be looking at a little video here on tracking rate. So first of all, just kind of ask some general questions here is, how do I know how fast a reaction is going? I mean, if we have a reaction that says, let's say, A plus B yields C, well then, how do I know how fast a particular reaction is going? How might I track that? We got an example of a candle here, but any reaction. So it turns out that really, when we track something, not everything is even, you can see very easily too. I mean, think of this as if you have a reaction in a beaker, okay, and let's say A and B are being dropped in here, and they're producing C inside this beaker. I mean, how do we know it? So it turns out that we're going to use like some characteristic. We need to track some sort of property in this case. So, some cases it might be like literally a pH meter. That could be an option. Some property could be light, color being shined through something. See, maybe C is pink. Okay. In this case, maybe C is a gas, and we can trap it, in a container. Maybe this reaction also takes in energy. I put it on this side. That's endothermic. So maybe we can track how much energy is going in and out with a thermometer, and we could track that way. There's lots of ways, but it's quite possible that A, B, and C could be completely colorless. Then, what in the world do we do? So this is the ingenuity of someone who's working in a lab or is a chemical engineer, that maybe they find a way to do another chemical reaction on the side, where they convert C, which normally is colorless, into something that's pink. So where there's a will, there's a way, but somehow we need a property at which we can measure. Okay. So let's say, for example, a candle. A candle, of course, how do we track the rate at which a candle burns? All of us have seen candles. Alright, they just look like this. You could track lots of properties. Again, this is not one way or a wrong way of doing this. It's just different ways. You could track, okay, maybe you could track the height of the candle. Maybe you could track now in class we'll do this a lot, but we'll track the mass of the candle. And literally, we could do a data table where you have the time versus the mass of the candle. If you had a little more tools at your disposal, maybe you could measure the heat coming off of this thing, energy, or the carbon dioxide, or the water. There's a lot of ways. Okay. So how might you track this thing? I think in class many times we've done this experiment where we just track the mass of the candle, okay, as it's described right here. But there's lots of ways. So what is the actual chemical reaction going on here? Well, so again, there are lots of different types of candles, obviously, but you'll see a little picture here before that. Typically, a paraffin wax, in its simplest form, is just a long carbon chain. And we're talking like upwards of 30 carbons long. And this has got London dispersion force is like up the yin-yang, right? So that's why it's a solid, but not very much. I mean, a little bit of heat, it liquefies quite easily. So this is our chemical reaction below here. You can write yours in here. So 30 carbons would be a 30 going right here. So the same number of carbons have to be here, has to be here. And then 62, so this is going to be what, 31 is going to give us 62. And now we need to say, okay, oxygen. Alright, so I need to get 31, so it's 31 oxygens here, plus another 60 oxygens here. And this is going to be 91 oxygens right here. Okay, I can't get 91 because it's an odd number. So we're going to just take this thing and we're going to double it. This is going to go to 60. This is going to go to 62. This is a big molecule. These numbers aren't that unheard of. So now, what do we need now? Rather than 91, we need 182. 182, which means you're going to need 91 oxygens. So this is a really long carbon chain, and for every 2 of these guys, you're going to need 91 oxygen molecules. You're going to get 60 carbon dioxide molecules and 62 water molecules. So 2 C30s, 862 plus 91 O2s gives me 60 CO2s plus 62 H2Os. This would be very similar to like diesel. It's a little shorter than diesel fuel, but similar. Alright, so this is the rate at which these things are being consumed and or produced. Okay. Alright, so let's keep moving here. So how do we track this? Does what we track matter? Okay. So let's take a moment here and let's just kind of look at this. In my candle situation here, I have my mass here. I'm just going to grab this here. And if we track this guy, or try and graph this guy, it's going to look like, well, first of all, we're tracking, depends what you're tracking. You can track mass. And as we've done this in class, you'll see, and of course you probably noticed, that a candle burns pretty evenly. This is something that should be quite obvious for someone who lives on Earth. But candles burn, and they burn at a pretty steady rate. They don't necessarily all of a sudden burn faster and faster and faster and faster, or slower, 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 slower. They just kind of burn at a certain rate, and that's why people like them. Okay, so in this situation, the rate at which the candle is being lost, okay, could be tracked at, let's say, something like this. I'm just really roughing this out. It's a 2 here, all right, the candle, and it's not being used in the same units either, so the candle might be looking something like this, very slowly. And then my oxygen is being consumed at a rate that is considerably higher, okay. This is just rate used here. And then the carbon dioxide and the water are both being produced kind of at the same rate, pretty similarly. So it might look something like this. And it's not quite something like that. Okay. So it turns out that everything just forms kind of a steady rate. Things might be being consumed in different rates, but this ratio here is locking everything. For every 2 of these, all right, let's grab something a little bit lighter, easier to see. For every 2 of these, I consume 91 of these. So everything's running under the same time frame. So in this situation, if I consume 2 of these in 1 second, I consume 91 of these in 1 second. Again, that 2 to 1 second, or 91 to 1 second, that's going to be holding true whether I'm doing 4 in 2 seconds or 182 in 2 seconds. So the rates, the relative rates here, hold constant. Relative rates. Now, what I'm referring to the relative rates is that essentially the rate at which the candle is leaving has to be locked to the rate at which oxygen is leaving, because of the 2 to 91 ratio. So the stoic ratio here will relate one thing to the other. So really all we need to do, does it matter what we track? And the answer is no. We can track anything on this thing, and we can relate that thing to something else. If I track the rate carbon dioxide is produced, you see examples in biology a lot where, let's say you have a tank and you have a little mouse inside this guy here, and you want to measure how well the chemical reactions inside this rat or little mouse are running. You could measure the metabolic rate of the mouse. How? Simply by putting a meter in here that measures carbon dioxide. And the more this guy breathes out carbon dioxide, the more this internal chemical reactions are running inside the little mouser. As long as you'd have to seal it so the carbon dioxide can't get in and out, okay? But you could that's saying, okay, if I track the carbon dioxide, then I can track all the other similar chemical reactions that are running inside of it. All right. So in this situation, I just add these things already, and this particular slide is a one where you can take a moment and just say, okay, this is what we did right here. I may have to remove that slide, we'll see. But either way, all my relative rates are being tracked on here. So if we know the rate at which one item is being a reaction, can we always figure out the rates for the other substances? And the answer is yes. And that's tied by the good old stoic ratio. Okay. So if chemical reactions X and Y started out at the same concentration, and Y is being measured to be consumed at 0.2 moles per liter per second. So what is, again, let's answer this question right here. What does that mean? Okay, well, it's a rate. So a rate is literally change, okay, per time. That would be kind of how we're dealing with a rate. And the rate in this case is M is moles per liter per second. And that is how we deal with this. This and this is the same thing. I really like to just show it like the moles per liter per second, because mathematically I like to be able to just move the individual units around, and I would strongly suggest using it this way. Because in this case, can sometimes be deceiving because, well, is the L on the bottom or is it on the top? It's the moles per liter per second, but really this is the same thing. Okay. So I would rather have it be moles per liter per second. Okay, what is the relative rates of the other substances? Okay, well, we know, again, the stoic ratio. So take a moment, pause it out, and let's figure out what the actual rates are. Okay. So in this situation, you should try it already. 0.2 is Y. So what's the consumption of X? Well, it's just going to be 0.2 at a 1-to-1 ratio equals 0.2, which the Z is being produced. And of course, this might look like simple work, but you got to show it, right? You got to show a person on an AP test what you're doing. And what's the rate at which the X is being consumed? Well, it's 0.2 at a 1-to-2 ratio is 0.4, and we might indicate this being a negative, meaning that it's being lost. Okay, and that's moles per liter per second. So take a moment, pause it, try out the graph. Okay, so once again, if we're doing the X and Y, this is something that is also indicated in equilibrium. So if Y is being consumed like this, then X should be being consumed like, let's get a different color here, X should be like twice the rate. And Z, or Y, Z, yep, should be going at a similar rate to that of Y. This is Z, this is X, and this is Y. Alright, so again, what does the slope represent here? Okay, what does this slope mean? Okay, whenever we do a slope, it's the Y rise over the run. Okay, so that would be the change in Y over the change in X. That's the change in concentration over the change in time. And that is, again, the rate. So my slope here is indicating to me what or how fast is this thing actually running. Okay? That's that graph. That's an important point of that particular graph. So let's take a closer look at the candle graph. Okay, and I just sketched this out, and you should have one kind out there. You have the mass of the candle decreasing, you got oxygen, you got carbon dioxide. These things are all kind of going like that. But what does the slope mean? Okay, I literally just talked about that. Okay, and again, let's reiterate that that is the change in this case, the mass or change in time. So that would be, again, a form of a rate. Okay. What happens to the rate as time goes on? Okay, now here the situation is kind of unique. That the rate is staying constant. Pretty constant. Because it's not changing. Would we expect all graphs to look like this? You know, for all chemical reactions? And the answer is, I don't think so, right? What would other graphs look like? Let's say, for example, what if there's a possibility that something could speed up as it went along? So that would be something that would look like this. All right, so if we're speeding up, it might look like this, where it starts out relatively slow, but it goes faster and faster and faster. Remember, the slope, this would be for a reactant, losing a reactant. The concentration of this thing is getting less. So the slope represents concentration. And then for another chemical reaction here, we might say, okay, well, maybe it starts out, so it slows down. All right, so in this case, there we go, looking at something like that. So are there examples of chemical reactions that that this would happen? Okay, well, let's look at this. For a slowdown, this is really, I would say, really common in everyday lives. I mean, you need two particles to collide in order to have a reaction. So what happens when there's less particles? Well, there's less collisions. Less particles, okay, means less collisions, which means less reactions. Okay, so that's really, really common in our everyday lives, right? What about a speed up? Okay, could something possibly speed up? And the answer, again, is yes. This can happen too. Let's say, for example, a nuclear reaction, where one item sets off a rapid reaction where it breaks in half, and then it breaks in half again and again. You can get an exponential type situation occurring. This is very common in a nuclear reaction. So going exponential. You might even think like a very instant when you light a match. Okay, in that very short time, it just starts slow and it really just explodes. So some combustion reactions might speed up, and there would be various reasons why it might speed up, but all of these situations could be something that might happen. So a candle burns. This is a sheet at this point in time is in our workbook, so I kind of want to walk through this quickly here. We got usually cut this off at about 20 minutes, so we got a couple minutes here. I'm going to walk through this. What is the rate of burning in a chemical reaction in grams per second? So all these things you should be pausing and trying on your own. So this is going to be what we refer to as an average rate, because we're taking a change for a large change in time. So the candle goes from, looks like we got a change in mass, that being change in time. The change in mass is going to be, it looks like about 2.5 grams, 2.5 divided by 5 minutes. And you're going to get your change, it's grams per minute. And they want per second, so you would need to then just swap this out for 60 times 5 is 300. So this would be in grams per minute, but 2.5 divided by 300 seconds would be 2.5 divided by 300 is 0.0083. 0.0083. That's grams per second. Of course, over the course of the reaction, okay, we did this in class, but we talked about it right here, it kind of remains constant at burns. How might the graph look different than in graph 1? Okay, we did this in class, so we're going to skip this question. It's in your workbook if you want to try that. We just talked about several types of graphs that are constant, okay, and one that might slow down and one that might speed up. You might think that a constant reaction might be kind of unusual too. But what is the overall order for this process? Because the concentration versus the time, or the concentration not affecting this, we call this a zero order. And if you're not familiar with that yet, eventually you will be. Student hypothesis: the rate constant equals the rate, and this will always be the case for rate constants. So we're looking at the rate constant for a zero reaction is the actual slope of this graph. And this particular video, of course, we're not talking about rate constants, but it's in and around our area. So the rate constant is equaling that. But in this case, for other chemical reactions, is this always the case? Answer is no, actually not. Alright, and then our final question here is just going to be this guy, and a pretty common question that might get interweaved into any other question, also on our workbook here, but you should go ahead and try this. Alright, so it says the hydrogen is being evolved at that rate, so what is the rate of consumption of the pH3? Okay, so it's just going to be a stoichiometric ratio question at a 6:4 ratio. This is the pH3, this is the H2, and of course you can go ahead and calculate that on your own. Thank you very much.